A 6-pulse rectifier with a delta Y transformer creates harmonics that contribute to excessive heating in the transformer. The output current of a 6-pulse rectifier contains harmonic components at frequencies that are multiples of the fundamental frequency, such as 50 or 60 Hz for power systems. The most significant harmonics are firstly the 5th harmonic, approximately 600 Hz, secondly the 7th harmonic, approximately 840 Hz, thirdly the 11th harmonic, approximately 1320 Hz, and fourthly the 13th harmonic, approximately 1560 Hz. The heat generated in the transformer is proportional to the square of the root mean square ohms current flowing through the transformer windings. Heat equals ohms squared times R, where ohms is the root mean square current and R is the resistance of the transformer windings. The harmonic components of the rectifier output current contribute to the ohms value and thus to the heat generation. The firing angle alpha of the silicon-controlled rectifiers, or SCRs, in the rectifier controls the conduction period of the SCR. As the firing angle increases, the conduction period decreases, and the harmonic content of the output current increases. Therefore, the relationship between heat and firing angle is inverse. Higher firing angles lead to higher harmonic content and increased heat generation, and lower firing angles lead to lower harmonic content and reduced heat generation. To determine the exact heat generation due to harmonics, you can use Fourier analysis to calculate the ohms value of the harmonic components of the rectifier output current. The heat generation can then be calculated using the formula above. Mitigation strategies include 1. Use a high-rated transformer to handle the increased heat generation. 2. Use a 12-pulse rectifier instead of a 6-pulse rectifier to reduce harmonic content. And 3. Install harmonic filters to suppress harmonics in the transformer windings. Considering the harmonic analysis of a 6-pulse rectifier, it's crucial to understand how these harmonics arise and their impact on the system, particularly concerning heat generation within the delta Y transformer. These rectifiers, commonly used to control direct current, or DC, motors, introduce harmonic currents into the power system due to the nonlinear operation. These harmonic currents are not merely theoretical concerns, they manifest as real-world problems, primarily excessive heating within the transformer. The harmonic components of the rectifier output current are found at multiples of the fundamental frequency, typically 50 or 60 Hz. While numerous harmonics are generated, the most prominent are the 5th, 7th, 11th, and 13th harmonics. To put this into perspective, in a 60 Hz system, these harmonics correspond to frequencies of approximately 300 Hz, 420 Hz, 660 Hz, and 780 Hz, respectively. These frequencies deviate significantly from the fundamental frequency and can cause a range of issues. Heat generation in the transformer is a direct consequence of these harmonic currents. The heat produced is proportional to the square of the root mean square, or ohms, current flowing through the transformer windings, represented by the equation heat equals ohms squared times R, where R is the resistance of the transformer windings. This relationship underscores the importance of minimizing ohms to reduce heat. The harmonic components contribute significantly to the overall ohms value. Each harmonic current adds to the total ohms, thereby increasing the heat generated. This additional heat can lead to premature aging of the transformer insulation, reduced efficiency, and potential failure if not properly addressed. The firing angle of the silicon-controlled rectifiers, or SCRs, plays a pivotal role in shaping the harmonic content of the output current. The firing angle determines when each SCR begins conducting, thereby influencing the duration and shape of the current waveform. As the firing angle increases, the conduction period decreases, and the harmonic content of the output current escalates. This inverse relationship between firing angle and harmonic content is a critical consideration in rectifier design and operation. When the firing angle is higher, the current waveform becomes more distorted, resulting in a greater proportion of harmonic frequencies. Conversely, lower firing angles lead to less distortion and a reduced harmonic present. The precise calculation of heat generation due to harmonics requires a detailed analysis of the rectifier output current. Fourier analysis is a powerful tool for this purpose. By decomposing the current waveform into its constituent frequencies, Fourier analysis allows for the determination of the ohms value of each harmonic component. These ohms values can then be used in the heat equation to estimate the heat generated by each harmonic. Summing the heat generated by each harmonic provides an estimate of the total heat generated in the transformer due to harmonic currents. Mitigation strategies are essential to manage the adverse effects of harmonic currents. Several approaches can be employed, each with its own advantages and limitations. Firstly, using a higher rated transformer provides a greater capacity to dissipate heat. By selecting a transformer with a high kilovolt ampere or kV rating, the transformer can withstand the increased heat load without exceeding its temperature limits. This approach is often the simplest and most direct, but it may also be the most expensive. Secondly, employing a 12-pulse rectifier instead of a 6-pulse rectifier significantly reduces harmonic content. The 12-pulse rectifier achieves this by using two 6-pulse rectifiers with a phase shift between them. This phase shift cancels out certain harmonics, resulting in a cleaner output current with fewer harmonic components. While more complex and costly than a 6-pulse rectifier, the 12-pulse configuration offers a substantial improvement in harmonic performance. Thirdly, installing harmonic filters is a targeted approach to mitigate specific harmonics. Harmonic filters are designed to shunt specific harmonic frequencies, thereby preventing them from propagating through the power system. These filters typically consist of tuned inductors and capacitors that create a low impedance path for the targeted harmonic frequency. By selectively filtering out the most problematic harmonics, harmonic filters can effectively reduce heat generation and improve power quality. In summary, understanding the harmonic analysis of a 6-pulse rectifier is crucial for ensuring the reliable and efficient operation of power systems. By recognizing the sources and effects of harmonic currents, engineers can implement appropriate mitigation strategies to minimize heat generation and maintain power quality. This involves careful consideration of transformer ratings, rectifier configurations, and harmonic filtering techniques. Now, let's delve deeper into the specifics of calculating harmonic distortion, mitigating its effects, and optimizing system performance. We can discuss the transformer's role in harmonic distortion, the impact of different transformer connections, and advanced filtering techniques. Transformers play a critical role in harmonic distortion within power systems, especially in applications involving rectifiers. The transformer not only steps down or steps up the voltage, but also acts as a pathway for harmonic currents generated by nonlinear loads like 6-pulse rectifiers. The design and characteristics of the transformer significantly influence the propagation and amplification of these harmonics. Different transformer connections, such as delta Y, delta delta, and YY, have varying impacts on harmonic currents. The delta Y connection is commonly used in rectifier applications because it provides a ground reference on the secondary side and helps to block the flow of zero-sequence harmonics. However, it can also contribute to the amplification of certain harmonics, particularly the fifth harmonic. The delta-delta connection does not provide a ground reference and is more susceptible to circulating harmonic currents within the delta winding. The YY connection is generally not recommended for rectifier applications due to its tendency to propagate zero-sequence harmonics. The transformer's impedance also plays a crucial role in harmonic distortion. The transformer's impedance limits the flow of harmonic currents. A higher impedance transformer will reduce the magnitude of harmonic currents but may also lead to voltage distortion. A lower impedance transformer will allow for higher harmonic currents but may maintain a better voltage profile. Advanced filtering techniques are often necessary to mitigate harmonic distortion effectively. Passive filters, consisting of tuned inductors and capacitors, are commonly used to shunt specific harmonic frequencies. These filters are designed to create a low impedance path for the targeted harmonic, thereby preventing it from propagating through the power system. Active filters, on the other hand, use power electronic devices to inject compensating currents that cancel out the harmonic currents. Active filters are more versatile than passive filters and can adapt to changing load conditions. Hybrid filters combine passive and active filtering techniques to achieve optimal performance and cost effectiveness. These filters typically use passive filters to handle the bulk of the harmonic current and active filters to compensate for the remaining harmonics and improve overall system performance. In addition to filtering, other techniques can be used to mitigate harmonic distortion. These include using harmonic mitigating transformers, which are designed to reduce the flow of harmonic currents, optimizing the firing angle of the SCR in the rectifier to minimize harmonic generation, and using power factor correction equipment to improve the overall power quality of the system. Furthermore, regular monitoring and analysis of harmonic levels are essential to identify and address potential problems before they escalate. Harmonic analyzers can be used to measure the magnitude and frequency of harmonic currents and voltages, providing valuable data for system optimization and troubleshooting. By implementing a comprehensive approach to harmonic mitigation, engineers can ensure the reliable and efficient operation of power systems, reduce heat generation in transformers, and improve overall power quality. The relationship between the firing angle and the harmonic content in a 6-pulse rectifier is a critical aspect to consider when designing and operating such systems. The firing angle, often denoted as alpha, determines the point in the alternating current, or AC, cycle at which the silicon-controlled rectifiers, or SCRs, are triggered to conduct. This angle directly influences the shape of the output voltage and current waveforms, and consequently a harmonic spectrum. When the firing angle is 0, the SCR conduct as soon as they are forward biased, resulting in a nearly rectangular output waveform with minimal harmonic distortion. As the firing angle increases, the conduction period of the SCR decreases, leading to a more distorted output waveform and a higher harmonic content. The harmonic content is typically quantified by the total harmonic distortion, or THD, which represents the ratio of the root mean square, or RMS, value of the harmonic components to the RMS value of the fundamental component. A higher THD indicates a greater level of harmonic distortion. The dominant harmonics in a 6-pulse rectifier are typically the 5th, 7th, 11th, and 13th harmonics, as previously mentioned. The magnitude of these harmonics increases with the firing angle. The relationship between the firing angle and the harmonic content can be mathematically modeled using Fourier analysis. The Fourier series representation of the output voltage or current waveform allows for the determination of the amplitude and phase of each harmonic component as a function of the firing angle. This analysis reveals that the harmonic amplitudes are generally proportional to the sine or cosine of multiples of the firing angle. In practice, the firing angle is often controlled to regulate the output voltage of the rectifier. However, increasing the firing angle to reduce the output voltage also increases the harmonic content. Therefore, a trade-off must be made between voltage regulation and harmonic distortion. Several techniques can be used to minimize harmonic distortion while maintaining voltage regulation. These include using pulse width modulation, or PWM, techniques to shape the output waveform and reduce harmonic content, employing active filters to compensate for the harmonic currents, and using multi-pulse rectifier configurations to cancel out certain harmonics. The choice of technique depends on the specific requirements of the application, including the desired level of harmonic distortion, the cost constraints, and the complexity of the system. In addition to the firing angle, other factors can also influence the harmonic content of the rectifier output. These include the source impedance, the load characteristics, and the presence of any imbalances in the AC supply voltage. A high source impedance can exacerbate harmonic distortion by causing voltage drops at the harmonic frequencies. Nonlinear loads can also generate additional harmonics that contribute to the overall harmonic content. Imbalances in the AC supply voltage can lead to the generation of even-order harmonics, which are typically not present in a balanced system. Therefore, it is important to consider all of these factors when designing and operating a 6-pulse rectifier system. Regular monitoring and analysis of the harmonic content can help to identify and address potential problems before they escalate. By carefully controlling the firing angle, employing appropriate harmonic mitigation techniques, and considering all relevant system parameters, engineers can minimize harmonic distortion and ensure the reliable and efficient operation of 6-pulse rectifier systems. Further exploration of the harmonic current flow within a delta Y transformer connected to a 6-pulse rectifier provides valuable insights into the mechanisms behind transformer heating and potential mitigation strategies. The delta Y transformer is a common choice in these applications due to its ability to block zero-sequence harmonics and provide a ground reference for the direct current, or DC, side of the rectifier. However, the delta Y connection also introduces a 30-degree phase shift between the primary and secondary voltages, which can influence the flow of harmonic currents. In the delta winding, harmonic currents circulate due to the nonlinear nature of the rectifier load. These circulating currents can be significant, especially for the fifth harmonic, which tends to be amplified in the delta winding. The magnitude of these circulating currents depends on the transformer's impedance and the level of harmonic distortion generated by the rectifier. In the Y winding, the harmonic currents flow to the rectifier load. The fifth and seventh harmonics are typically the most dominant, but higher order harmonics are also present. The magnitude of these harmonics depends on the firing angle of the silicon-controlled rectifiers, or SCRs, and the characteristics of the DC load. The harmonic currents in both the delta and Y windings contribute to the overall root mean square, or RMS, current flowing through the transformer, which in turn determines the heat generated in the transformer windings. The heat generation is proportional to the square of the RMS current, as previously mentioned, so even relatively small harmonic currents can have a significant impact on transformer heating. To mitigate the effects of harmonic currents, several strategies can be employed. One approach is to use a transformer with a high kilovolt ampere, or kV, rating to handle the increased heat load. However, this may not be a cost-effective solution, especially if the harmonic currents are very high. Another approach is to use a harmonic mitigating transformer, which is designed to reduce the flow of harmonic currents. These transformers typically have a special winding configuration that cancels out certain harmonics, thereby reducing the overall RMS current. A third approach is to install harmonic filters on either the AC or DC side of the rectifier. These filters are designed to shunt specific harmonic frequencies, preventing them from propagating through the power system. The choice of filter depends on the specific harmonic frequencies that need to be mitigated and the characteristics of the system. In addition to these strategies, it is also important to ensure that the transformer is properly sized and protected. The transformer's insulation should be able to withstand the increased heat load, and the transformer should be protected against overcurrent and overvoltage conditions. Regular monitoring and analysis of the transformer's operating temperature and harmonic levels can help to identify potential problems before they escalate. By carefully considering the harmonic current flow within the delta Y transformer and implementing appropriate mitigation strategies, engineers can minimize transformer heating and ensure the reliable and efficient operation of rectifier systems.